going to try the methods of the tree method and the estimating method with perfect cubes. And can we translate what we know worked for perfect squares to work also for perfect cubes? Well, let's find out. Let's see if using a factor tree helps organize the prime factors for the number 729. And then we will group them in the same way that we did with perfect squares. So because this ends in 9, I'm going to start with 3. So I'm going to divide by 3, and that gives me 243. And then I'm going to divide that again by 3, and I get 81. Now, 81 divided by 3 gives me 27. 27 divided by 3 gives me 9, and 9 breaks out into 2 3s as well. Now it's giving me 1, 2, so there's 1, 2, 3, 4, 5, and 6. 6 3s, so I'm going to write them down. 3 times 3 times 3, and I got times 3 times 3 times 3. So if I group these, I have a group of 3 and a group of 3. 3 times 3 times 3, that's 27 times 27. So that means I have squares, or because I'm looking for cubes, I'm going to group them in 2, 2, and 2. So I have 9 times 9 times 9. So 729, is sort of an anomaly kind of number because it could be a perfect square, 27 times 27. But because I was asking for perfect cubes, it actually is 9 cubed equals 729. So just by grouping, I hope you see the difference on how we can change it from perfect square to perfect cube. Not all of them work out like 729. So let's look at the example of 2744. So this one's going to look a little bit different. So let's have a go at this one with the tree. Because it ends in 4, I'm going to start with 2 as my first prime number. That gives me 13. Oops, 1372. I'm going to break it down again by 2, and that gives me 686. Break it down again by 2, 343. Now, 343 obviously does not divide evenly by 2. I could try 3. You will find it doesn't work. Doesn't work with 5, so the next prime number is going to be 7. And that does work. And then 49 is 7 and 7. So now I'm going to write these down. I'm going to group them because I have 3 2s. So I have 2 times 2 times 2. And then I have 3 7s, 7 times 7 times 7. So because I want 3 groupings, I'm actually going to take one of each, and then the second one, and then the third one. So I'm going to group them 2 times 7 times 2 times 7 times 2 times 7. So I have my groupings. It's 14 times 14 times 14. So that gives me 14 cubed equals 2744. Now, what happens if we're asked to do it by the estimating method? Well, let's look at 1728 for our example. Now, with 1728, I am going to do it by estimating. I'm actually going to do the similar fashion that I did with the squares, is I have to figure out what cubed is close to 728. So I'm going to start with my first guess or try. Okay, my guess, I know that 10 cubed is 1,000. I also know that 20 cubed equals 8,000. Those two I know for sure. Now that means that 1,000 is between 1728, so it's less than 1728, and 1728 is less than 8,000. So again, it's got to be somewhere between these two numbers. I also know that 10 cubed is less than the cubed root of 1728, which is less than 20 cubed. Now, looking at the number, 1728 is closer to 1,000 than it is to 8,000. So I'm going to stay closer to 10 for my guesses. So now I'm going to use my full guess, my guesses. So I'm going to try, to start off with, I'm going to try 11 cubed. Try 11. So 11 cubed is 1331. This number is too small, but it's close. My guess, I got somewhat luckier on my first try because 11 cubed is pretty close to 1728. So my second try, I'm going to try 12. And 12 cubed gives me 1728. This is correct. So, woohoo, winner, winner, chicken dinner. 12 cubed is the correct answer. So by estimating, I have to pick a number between what I know. And if you notice on both the perfect squares and perfect cubes, I chose whole numbers that were easy to do in my head. So I know that 10 cubed is 1,000. 20 cubed is 8,000. 30 cubed, 9,000. They're pretty easy to remember. If you have trouble with those, these are ones that you should be memorizing. So something to think about, adding to your cubed chart.